All right, let's go through these problems here on this worksheet. I'm just going to talk about whether it's true or false, and then the counterexample. You could rewrite them multiple ways. So if you have questions about the way that you rewrote it, I can certainly explain that to you or whatever individually, but I think the rewriting, I'll let that up to you to rewrite it in your own way, because it could be written multiple ways. So like I said, I'm just going to talk about true or false, and then give you if it's false, I'll give you a counterexample as to why it is false. So let's look at this first one here. A critical point or a critical number of a function f of a variable x is the x coordinate of a relative min or max and the value of a function. Now, if you read that quickly and you kind of think, okay, yeah, that makes sense, which it may be kind of true, but it's not completely true. So this one is going to be false, and the reason is because a critical point or a critical number is not always a max or a min. And if you remember, it could also be where the derivative was undefined, or it could also be something like this. Okay, you could have a function like this where this value right here would give you the first derivative being equal to 0, but that is not a critical value because it's, I'm sorry, it is a critical value, but it's not a max or a min because the function is increasing as it goes up through it. So if you had something like, x to the third, a function like that would have a derivative at 0, which would be a critical value, but it's not a max or a min. Okay, so you, again, reword that how you want. Second one, continuous function on a closed interval. So let's say here's my A, here's my B. Can only have one maximum value. A continuous function on a closed interval can only have one maximum value. Now, if we have a continuous function on this, you could have something that looks like this. Well, I'll try and look at something like that, okay? So what you want to think about is, okay, there were two critical values here that gave you, let's say that this was at 2, right? And this was 1, and this was 3, or something like that, right? So you might think of this and say, well, that's going to be false because right there's two maximum values. There's two spots where it gives you a maximum value, but those maximum values would be the same. So it does have one maximum value. That maximum value could be repeated, but it can only have one maximum value. Okay? You can't say the maximum value is at 2 and the maximum value is at 3. Your maximum value would only be at 3, but that maximum value could happen more than once, but it is still only one maximum value. Okay, so hopefully that makes sense. So this one is true. I don't know if I actually said that. That one is true. All right, number 3, second derivative is always positive. If the second derivative is always positive. So let's think about that. What does that mean? If the second derivative is always positive, well, that means it's concave up. Then the function of f must have a relative min. Okay, now the common misconception here is that we think, okay, well, if it's concave up, it's got to look like this, right? But that's not always the case. That sometimes is the case. And in this case right here, it does have a relative min right there, whatever that c value would be. But again, we're trying to think of a counterexample. So can we think of a function that is always concave up? So the second derivative is always positive, but it does not have a relative min. Now, the only thing that I can think of is, if we see a function like this, and this one may be a little bit more challenging for you to think about because we haven't looked at the derivative of exponential functions. But if we have an exponential function like this is concave up everywhere. It's always positive. Second derivative is always positive. But this does not have a relative min because it's continuing to get smaller. It's never going to reach 0, but it continues to get closer to 0. And again, that one might be a little bit tricky for you to realize why this is false. And that's mainly because we haven't done the derivative of e to the x yet. So yeah, we'll talk about that more when we get into chapter 5 and we do exponential and logarithms. All right, number 4. If a function has a local min value at x equals c. So if a function has a local min value at x equals c. So let's go over here. I always do stuff on that side. So here's c. So let's say I have a local min right here. Does that mean that the first derivative is 0? Again, I'm trying to think of something where this does not work. So if I'm trying to think of something that doesn't work, think of a function where the first derivative doesn't exist, but also has a minimum value at c. So what I think of is an absolute value. Okay? So if we have an absolute value here, the minimum value would be at c, but the first derivative is not equal to 0 because the first derivative actually doesn't exist there. Okay? So that's something else to think about. We could also think of, let's say if we have another, let's just call this an x value. It could also work if we had like a piecewise function and we had something like this. Okay? And this is an open circle right here. This derivative, this would be a local min, that's the smallest value right there. But also, the derivative doesn't exist here at this x value because on the right-hand side and the left-hand side, those limits don't equal each other, so that would not exist as well. But I think probably the more common answer would be this absolute value function there. So this one's false. Sorry, I should be writing that down first. False. All right, number 5. If the derivative of 2 is equal to 0. So here we are at 2. Again, whoever made up these worksheets must love the number 2. First derivative of 2 is equal to 0. And the second derivative is negative. So we have a 0 here and it's negative. So we know all around it has to be negative. We don't know what's happening. I shouldn't have drew that arrow on there because we don't really know what's happening there. Then x locates a relative max. So this one is true. Again, with these two things together, this one would be true. The first derivative is 0. Second derivative is always negative. Means we would have something that looks like this. Okay? So number 5 is true. Number 6. So, if the second derivative of 2 is less than 0. So here we are back at 2 again. So the second derivative means this whole thing is concave down, right? So the whole thing is concave down here at 2. X equals c is a point of inflection. Actually, let me back up. I kind of drew my point of inflection there at 2, or my critical value there. Let me just change this. Let's say if we have something like this. There we go. Okay, we got something like that. We want to know is x equals c. So let's say my c value here is 0 in this one. Is that a point of inflection for the function of f and cannot be the x-coordinate, the max or min point on the graph? So if we think of a function here where the second derivative would be negative, second derivative of negative, it being equal to negative, but also we have some c value that is 0, okay, and it's saying it cannot be a max or a min. So I'm looking at this value right here giving me a second derivative of 0, but it would be a max or a min. So is there a function where this exists? Okay, the second derivative here at 2 is less than 0. That's concave down. But is there a function that when I look at the second derivative here at c, it is, to go against the cannot, it can be a max or a min? So if we think of these are all parabolas, these are all even powers, but we can't just say x squared. We have to go higher than that. But if you say like, I don't know, x to the 6th, take the second derivative of that, the second derivative would be a point of inflection, but then it also would be your max or a min. Okay, so this one is false. All right, 7. If a function f is defined on a closed interval, f prime is positive, so it's always increasing. So first of all, let's start with our graph of a closed interval, right? We're looking at a closed interval. So whatever, here's closed interval from a to b. And the derivative is positive always. So wherever it starts down here and it ends up here, it's always, the derivative is always positive. So it's not going down or equal to 0 at all. It's not flattening out or going down. Then the absolute max of the function will occur at the right endpoint, right here. So this one is true. Okay, so number 8 says the absolute minimum value of a continuous function on a closed interval can only occur at one point. So this is similar to, I think it was number 2, where number 2 said a continuous function on a closed interval can only have one maximum value. So it's kind of like the same thing there, where we're looking at a closed interval from a to b, and this says it can only occur at one point. So, and it's really just knowing the difference in the wording between one value and one point. So 1 point is referring to an x value. When you see like 1 point, like think of like a critical point or a, like a critical point or whatever. And then in number 2, when it said can only have one maximum value, that's referring to the y value. So so this one is just the opposite then, and this one would be false. And if you think of like any kind of function that would have some values that where it would go up or down or whatever, and the same y value would occur at 2 different points. Okay, so like if we have some point here at like 2 and some point over here at 4, something like that. So this can occur at 2 different points, but it would still only have the same maximum value. So there's just a little bit of a difference there in the wording. So number 8 would be false. And if you think of a counterexample, if you just think of something like the sine function, if you think of the sine function as you look from 0 to 2 pi, or 0 to 4 pi or something like that, where it's going to repeat itself, it would have the same y value occurring at 2 different points, like pi over 4 and 3 pi over 4 would both give you square root of 2 over 2. They would have the same y value. That wouldn't be a maximum value, though. That's kind of a bad example. If you think of like pi over 2 would be 1, and then if you repeat that and you come back around to 3 pi over 2, or not 3 pi over 2, you would have to add 2 pi to it. So 5 pi over 2, they would both have the same maximum value at 1. Again, that's on a closed interval. You could have multiple points that give you the same y value. So 8 and 2 were kind of asking similar things, but one's referring to the x value and one's referring to the y value. All right, number 9. If x equals 2 is the only critical point of a function, so that just means that there's only one value in the first derivative that gives you a 0, and that happens at 2. So if x equals 2 is the only critical point of f, and the second derivative of 2 is greater than 0, so let's just say if we have, here's our critical point at 2, and the second derivative is positive, so again, keep in mind that's the only critical point, so that would be the only spot where it either flattens out or has a, in this case, minimum because the second derivative is positive, then f of 2 is the minimum value of the function. And again, this would have to be the minimum, and whether you're looking at relative or absolute minimum, it's the only spot where there is a critical point in f. So that's the only value where this function would have a derivative of 0. So if it was just one of them, and it didn't say it was the only one, if it was just one of the critical values, you could have something like this that would have, a critical value here and a critical value there, and then those two would give you different critical values. So then it wouldn't necessarily be the minimum value of the function because the graph could go down, and you would have some minimum values over here on the side. So, but in this case, 9 is true. Okay, number 10. To locate the absolute extrema of a continuous function on a closed interval, you need to only compare the y values of the critical points. And the important part here is it says on a closed interval. So if you remember when we did these before, if we have a closed interval, we not only include the y values of the critical points, but we also include those endpoints. That should be a closed interval, sorry. We also need to include those endpoints A and B, so this one would be false. Okay, it's not only the y values, we also have to include the endpoints of our interval to find the absolute extrema. So 10 is false. All right, number 11. We have the first derivative of c is equal to 0, and f prime, so here's my c value, f prime decreases through c. So that means there was some negative values on the left and negative values on the right. So you think of like a negative x cubed function, like the something that starts in the upper left and goes down through c, flattens out at c because we have a derivative equal to 0 there at c, and then continues down where it says the first derivative decreases through c. Locates a local min. So this would not be a local min. It is a critical value. It does give us a first derivative of 0, but it's not a local min because the left is going up and the right is going down, so this would not have a local min, or really an absolute min because it continues down forever. So this one is false. All right, last one, number 12. Absolute extrema on a continuous function, or of a continuous function on a closed interval, can occur only at endpoints or critical points, and this one basically goes back to what we had talked about in, what was it, number 10? Yeah, in number 10. And this one would be true because that is now including all of the stuff that we need to. It can occur only at endpoints or critical points, okay? And again, we're talking about the absolute extrema, so maxes or mins. We're not talking about, the undefined values, but just the absolute extrema, maxes or mins. They occur either at the endpoints or at the critical points in between those endpoints. So 12 is true. All right, so a couple of problems from your book to try. 1 through 4 is matching the graph with the derivative graph, and then 7, 13, 29, and 37, there's just 4 problems to practice with the curve sketching stuff that we were doing in the notes earlier this week. And then the other thing I wanted to talk about was just kind of like intro to what we're doing in section 3.7. So this might be a little blurry if I enlarge it, but let me just show you. So 3.7, what we're going to end this chapter with is optimization. And optimization is basically like, so here you can see there's 5 different cubes with the top missing. And it's basically like all of these figures have the same amount of like surface area. Like they're using the same amount of material to create these boxes with no lids. But the question that we're going to ask, or we're going to answer in the next section is like, which of these boxes would produce the most space inside or the most volume? So we can practice or we can check this with a couple of different examples here, like you can see that are done in these 5 examples. But we've only tried 5 of them. We didn't try all of the options that give us the same surface area but different volumes. If we look at the ones we have here, we can see that this volume of 108 with a 6 by 6 by 3 would produce the most space inside, but it doesn't, these are not exclusive. This is not like the entire list. So we would have to, figure out, well, how can we do this? How can we determine what is the most area, or I'm sorry, the most volume that can be formed by using the same amount of surface area? So that's kind of just a little lead into what we're going to be doing tomorrow in the notes for section 3.7 is just this whole concept of optimizing different problems, whether it's a volume or optimizing the area or different things like that. There's all sorts of different scenarios that we can work with for optimization problems, and we're going to spend a couple days on that. So that was just a little bit of an intro to what we'll be doing in 3.7.